Hi, welcome everyone. This is the IPFS weekly call for Monday, the 9th of September 2019. I am Aching Brain. I will be your host. Today we're going to have a talk from Dirk on the Bitswap Protocol and upcoming improvements therein. I've just added the notes to the chat, so if there's anything else that you'd like to cover today, stick it in the agenda. If I could have a note taker, please. Someone. Oh, Lisa, good news. Your name's actually in the notes already as note taker because I just copy and pasted it from last week. So I've saved you some typing.
Outrageous.
Right. Does anyone have anything to add to the agenda, or shall we skip straight on to the good stuff? No, Terry, the floor is yours.
Yeah. So in case anyone is on this call who hasn't heard this spiel before, offline camp got rescheduled. It's coming up September 27th to 30th in Oregon on the west coast of the United States. So if anyone is interested in the offline first movement or how the connection between DWeb and making apps work offline and in low bandwidth use cases, Molly and I will be there. I'm looking around the screen to see who else on here. A number of other folks from the IPFS community and people.
Michael will be there, right? Michael Burns.
Michael Burns, yes. Oh, yes, I can see his fiery axe guy. Yeah, so a few of us will be there, and we'd love to have more company. We still have a few tickets left, and there are scholarships left. So I will paste the link in the chat and then over in the notes as well. Thanks.
Cool. Anyone else?
Yeah, that's great. Thank you very much. Cheers. Bye.
Nope. Take it away, Dirk.
Alrighty. You guys see my screen?
Can see your face.
Oh.
Nope.
Let's try this. How about now?
Yes.
Yeah.
Cool. All right, so for people who don't know me, my name's Dirk. I work at Protocol Labs. And today I'm going to be talking about Bitswap. So let me get my pointer here. So Bitswap is the way that IPFS gets stuff from the network. So either it'll ask for for blocks from its local block store, or if it can't find them there, it'll go and ask Bitswap, and Bitswap will go out to the network. So just a bit of background. When IPFS asks for stuff from Bitswap, it typically does it in a couple of main ways. So one way is that it requests a whole file full of stuff. So typically it'll request the root block. The root block contains links to child nodes, and then those child nodes contain links to further child nodes. So the request pattern will be ask for one block, ask for a few blocks, and then ask for many blocks. The other main way that it requests blocks is by asking for a path. So for example, when it's requesting a page on a website, it'll ask for the root, and it'll check the links to find page. Then once it's found page, it'll check the links to find doc.html, and then it'll fetch all the blocks in that document. So the request pattern here is request one block, request one block, request one block, request many blocks. So in use cases where we have a pretty high fan out, so like in Wikipedia or for a web page, typically there'll be a few nodes in the network that have all of the information, like the servers that are serving it originally. And then there'll be many nodes that have parts of the tree. So when a user's browsing through it, they'll download different bits for different documents within the website. So there's just kind of a visualization on the right where you can see 3 different peers, which each have different parts of the tree. So how do we find stuff? So Bitswap, the first thing it does, all of the peers it's connected to, hey, send me the block for the root. We call this a want. So it sends a want request to all of these connected peers. If nobody has it, then it asks the GHT, hey, who has this thing? Who's the provider for this block? Once someone responds, or a few peers respond, we add them into something called a session. So typically we'll ask, typically the same peers are going to have related blocks, like a whole bunch of peers will have the same file. So a session just gives us a way of keeping all the peers together so that we can make any subsequent requests to the same group of peers. So we have this concept of want lists. So in this example, peer A wants CID 1 and CID 2 from peer B, and peer B keeps a local copy of which CIDs that peer A wants, or which blocks peer A wants. Once peer B receives the block for CID 1, let's say, or maybe it's in its block store already, it sends that block to peer A, and it removes the want from its local copy of peer A's want list. So these want lists are maintained for as long as the peers are connected, and then they're discarded. We also have a cancel message. So in a similar example, let's say peer A has sent a want for CID 1 and 2 to peer B, and then peer A receives the block from someone else. Then peer A tells peer B, hey, I don't need this anymore, and peer B can remove it from peer A's want list. So how do we know which CIDs to send to which peers? Basically, peers in the session are ordered by latency. And when we get a request for a bunch of blocks, we split that request across the peers. So in this example, we have a split factor of 3, meaning there's 3 rows here. And CIDs 0, 3, 6, and 9 will each be sent to peers A, D, and G. CIDs 1, 4, 7 to B, E, and H, and CIDs 2, 5, and 8 to C and F. So as you can see, so a single want is sent to multiple peers. So in that case, we may get the same block back from multiple peers. We call that a duplicate. So if we start getting a lot of duplicates, then we change the split factor. So in this case, we change the split factor to 5. There are 5 rows. And as you can see, each CID is now being sent to less peers. So CID 0 gets sent to A and F, 5 gets sent to A and F, and so on. If we find that we're missing blocks, we're getting timeouts, or we're only getting uniques back a lot of the time, then we change the split factor again so as to send each want to more peers. This is how it currently works. Finally, we have a concept of rate limiting. So each session has a rate limit of 32 live wants. And a live want is just a want that we've sent out saying, hey, we want this thing, but we haven't heard back from anyone yet saying that they have it. So in this example, we have 8 pending. So let's say we get a request for 8 blocks from IPFS. So we max out the live want queue. In this case, for the purposes of this example, our live want queue has a limit of 4. So we put 4 blocks into the live want queue. We send them out to the peers. We get 2 blocks back, in this case CID 0 and 2, so they're now complete. And so we now have space to move 2 blocks from the pending queue into the live queue. So what are some of the issues with the current Bitswap implementation that we want to address? One is that peers are ordered by latency, when in fact what we really want is to order peers by throughput, so as to maximize bandwidth. Also, a request is split across peers, but oftentimes we'll only get a request for 1 or 2 blocks at a time. And this can also happen when, as in the previous slide, there's only 2 slots available here. So it doesn't really make sense to split such a small number of wants across our peers. It only really makes sense to do, excuse me, to do request splitting across when we have a lot of wants. So what we want to move towards is what we call streaming wants, meaning treat the wants individually instead of as a group, and then select peers on a probabilistic basis. Another issue we have is that wants are rate limited per session, and really we don't want to overload peers, so we want to rate limit them per peer. So for example, on the gateways, we have thousands of sessions. And finally, it's a little bit inefficient to always be getting duplicate blocks back when we're doing discovery. So we want to have a way of figuring out where stuff is without having to get blocks. And we also want to try to keep peers busy, meaning always make sure that peers have stuff to send to us so that they keep the pipe full to optimize bandwidth usage. So Stephen and I kind of got together and we came up with a few protocol extensions. So this is sort of a bit of a work in progress at the moment, but I'll tell you what our current thinking is. So we have this, we've added a new message called a have message. So basically this allows a peer to say, I have this block, but not to actually send the block. So this is particularly useful for discovery. So in our example over here, peer A, peer A sends a want have message saying like, hey, do you have this CID to peers B, C, and D? Peer B says, yep, I've got it. So peer A says, okay, now give me the block. Meanwhile, peer C and D just say, oh, I have this block as well. And then peer B actually sends the block back. In the case where the block is small enough as an optimization, we can skip the have part. So peer B will just immediately send back the block. So the second protocol extension we added was the don't have message. So currently, in order to know whether a peer has a block, we just have to ask for the block and then either get the block back or wait for a timeout. The don't have message allows the peer to immediately signal us and say, actually, I don't have this. So this allows us to very quickly determine the distribution of blocks that we want. So in this example, this slide's a little complicated, but I'll try to explain it. So let's imagine that we want to request 8 blocks. So IPFS has asked Bitswap for 8 blocks. Bitswap knows about 3 peers, B, C, and D. So it asks peer B for the first 3 blocks, and it says for the rest of them, hey, just let me know if you have this. Then it asks peer C for blocks 4, 5, and 6, and for the rest of them says, just let me know if you have it. And finally, for peer D, it asks for the last 2 blocks and says, let me know if you have the others. So then all of the peers respond and they say, I have this block, I have this block, I don't have this block, I do have this one, but I'm not sending it yet. And so it just kind of allows us to efficiently get blocks and also figure out where the blocks are if the peer we were expecting to have it didn't have it. Is that clear? Does anyone have any questions? Okay. One more extension we added was to have an outstanding queue size. So this is when, let's say I have requested a bunch of blocks from a peer. The peer is sending me back a response, but not all of the blocks can fit into each message. So Bitswap will actually round robin its responses for fairness. So it won't just send all the responses to the first guy, all the next responses to the second guy. It'll send a few responses to each of the peers that is requesting, and it'll kind of round robin until it's finished. So in this example, we've requested 8 blocks from our peer. The peer is able to fit 3 blocks into the message, the response message, which is of a limited size, and there are 5 blocks left over. So it just tells us, hey, there's 5 more coming. So we kind of monitor this queue size, this outstanding queue size, and if it gets too high, then we know we can back off. So this allows us to kind of like request a whole bunch of stuff, but not to overload the peer. So those are the protocol extensions. Now I'm going to talk about some changes to the actual implementation. So as I mentioned before, we can ask for a block, and at the same time as we're asking for the block, we can also ask if the other peers have the block, just in case this peer doesn't. So let's say that in this case, peer B responds and said, actually, I don't have this block, but peer A says that it does have the block. We can just directly go and ask peer A for it. So given that we want a block, how do we choose which peer that we're going to send that want to? So as I said, this is kind of an open question at the moment, but our current thinking is we're going to prioritize peers that have told us they have the block. We're going to prioritize peers that we know are a provider for that block. We're going to ignore peers that say they don't have the block. And then given all those things are equal, then next we order the peers by their have-don't have ratio, meaning if a peer has already told us that it has a bunch of the blocks that we were looking for before, then it's pretty likely to have the next block we're looking for. And finally, we select peers with the shortest queue. So each peer has a kind of queue of blocks that we're sending to it, or requests, I should say. So kind of tying this all together, if we have a whole bunch of wants and we have a whole bunch of peers, how do we decide which want to send to which peer? So in our example here, we have peers A and B. We have wants for blocks 0, 1, 2, and 3. So peer A has told us that, peer A has told us that it has CID 3. Peer B has said it has CID 2, and it does not have CID 0. And we don't have any information yet about who may have or have not CID 1. So we figure out what's the maximum potential that we can gain for each peer for each block. So here we're kind of saying, we're assigning a value saying that if we send CID 3 to peer A, we're expecting with a probability of 0.8 that peer A is going to give it back to us because it said it had it. So in this case, 2 peers have said that they have these 2 blocks, so these have the highest potential gain, 0.8. And then in order to choose between those 2, we simply do it by the order in which those blocks were requested. So CID 2 was requested before CID 3, so we end up sending sending a want for CID 2 to peer B. So that's pretty much it. As I said, we're kind of working through a few design questions. This involves me, I've written a proof of concept, and I'm doing a bunch of benchmarking, working with Stephen on that. There's a couple of open design questions that people might be interested in discussing on our issues board. So one design question is, given that peers are telling us how backed up they are, how much stuff they have to send to us, how exactly do we vary the size of, or the amount of stuff, the amount of wants that we're sending to them? That's an open question at the moment. And secondly, how do we vary the number of want blocks versus want halves? So here, should we send a want block to both peer A and BC, and then a want have to peer C? Should we just send a want block to peer B, and should we send want halves to peer A and C? What if we have, 50 peers in the session? Do we send a want have to all of them? That's kind of like an open problem that we're working through. And that brings me to the end. So does anyone have any questions?
How is the benchmarking looking? Have you got any interesting stats?
So it looks good. I don't want to say too much more because I haven't implemented all parts of it. So I don't want to sort of state any solid facts before we've done a full implementation, because I don't want to say like it's a lot better and then we discover that actually once we've completed the implementation there's a couple of things that make it a little bit slower. But in summary, for particular use cases, it works a lot better. For example, when the blocks are dispersed across a lot of different peers, this protocol makes it a lot faster to retrieve all the blocks, and we get a lot less overhead because we can quickly discover where they are. In certain cases, it doesn't actually make that much difference, and in certain cases, it does. It depends on the use case. Other questions?
Hello, it's Yanis.
Yanis.
So you mentioned that you changed right now you're picking a peer based on the latency, and that was changed to throughput.
Yeah.
Right? So what was I mean, have you thought of having both of them and assigning some weight in order, because latency is also important. I mean, it's difficult to say which one is more important, basically.
Yeah. So I think basically what we want to maximize for is how much stuff we're getting back from a peer. And so what we're kind of trying to do is always keep the pipe full. So we're sort of maximizing for throughput rather than for bandwidth or for latency. So it's quite a tricky problem to measure exactly what bandwidth is. And even measuring latency is actually quite tricky a lot of the time because it varies. So what we're trying to do is simulate, or we're trying to react as well as possible to existing network conditions, which can vary over time. So if we sort of keep the pipe full, then we can do that without really having to do too much calculation or having to think about it too much. It sort of happens organically. Does that sort of make sense? Stephen, do you want to expand on that?
Basically, we're not optimizing for like bandwidth usage of a specific peer. It's more that like we're optimizing for our own throughput and then like toggling the only things we can toggle. Instead of like in the past, what we're trying to do is like pick the peers that responded the fastest, but that didn't actually mean that they were like the fastest overall. Or like, I don't know, like at the beginning they could appear to like be returning blocks really quickly, but then like they get bogged down because they have to load through or something like that. So basically we're just like, we're trying to not model the network as much as possible, and instead just like optimize for what we want and then tweak the variables we have to try to like optimize that, if that makes sense.
Yeah. Yeah.
So,
No,
yeah. Go ahead.
Yeah, it does make sense. It depends a little bit on what is the kind of application that runs possibly behind. So, I mean, sometimes, if you have a big file, then this makes perfect sense. But then if you're delivering video or something, then the opposite might be, I mean, it's a classic problem of mice and flows, and
it depends on what we're looking for. But like, it's like if we're not resolving an initial block that's like a one-off, then we would want to optimize for latency. Often, like when you just like go and fetch a random block, you don't even know who has it. It's like I fetched this yet. Yeah. So basically, here we're literally trying to like, we call it max out the pipe. We're just like trying to find a way to keep all of our peers busy sending us data. So this will give us the maximum throughput. It's not. Yeah, you're right. Like if you had use case, like you open a session and then like you just like ask for a block and then you wait a bit. Then you ask for the block, then you wait a bit. You ask for the block, and wait a bit. Then you really want like the peer that returns the block the fastest. This would be something we would have to like measure internally, and then like we have to balance this basically.
Yeah.
We have to detect like we're asking for a lot of things, optimize for throughput. We're asking for like one thing at a time, optimize for latency.
Yeah, exactly. So it could be something more sophisticated because normally there is difficult to find one size fits all.
Yep.
Yeah. Okay.
Yeah, that's a good point.
That makes sense. Thanks.
Any other questions?
Cool. I guess that wraps up the weekly call then, if there are no more questions. Thank you very much for joining us all. This has been the IPFS weekly call for the 9th of September 2019. I've been Aching Brain. Dirk's been amazing. Thank you very much. See you all next week. Bye.
Bye.